Hi everyone, so welcome to my talk. I will present my work binary level with the fuzzing for use after freeze vulnerabilities. So this joint work with Sebastian, Matthew, Richard and Roland. So fuzzing is a simple but very effective testing technique to detect various kinds of bugs in real-world programs. So the idea behind fuzzing is to generate a huge number of random inputs uh, is the hope of crossing the tested programs. So AFLGO is the most popular fuzzer, and big companies like Google and Microsoft developed their own fuzzer to find bugs in their products and also in open source programs. Carriage-guided Greybox fuzzing like AFL and LeafFuzzer actually leverage the code carriage to guide the search. So by inserting instrumentation code to a programs, the fuzzer can keep track the execution flows exercised by an input and then determine whether an input cover a new part of the tested programs, and then the power schedule determines how many of mutant produced from the selected input. And in this case, we interested in the crossing input. While carriage-guided Greybox fuzzing aim to explore as many states as possible in the programs, directed Greybox fuzzing aim to perform stress testing on pre-defined potentially vulnerable target location like recent code changes or vulnerable function like string copy. So as you can see in this workflow, the directed Greybox fuzzing also take the targets as input, and then it uses a distance guided metric to actually guide the search at runtime. So the distance is pre-computed at the instrumentation phase between each basic block and a set of targets, and then the directed further favor inputs that are closer to the target. There's several security applications of directed fuzzing. In this paper, we focus on the two applications. First, the bug reproduction. So because there's only 55% bug reports are reproducible due to the lack of the proof of concept input and the different environments. So in this case, the developer cannot reproduce bugs. And the second application is the post testing. So developers are under a lot of pressure to get patches out quickly. So this can lead to poor patch qualities or regression bugs. So depending on the application, so target originate from bug trace patches or static analysis report. So despite tremendous progress in recent years, so current Greybox fuzzers still have difficulties in detecting complex vulnerabilities. So here we focus on use after freeze. So this kind of bug appear when a heap element is used after having been freeze. So the number of UAF bugs has increased in National Vulnerabilities Database, and they are currently identified as one of the most critical exploitable vulnerabilities and have serious consequences like data corruption, information leak, and denial of service attack. But why is this thing used after freeze hard? So there are two main reasons. So the first reason is complexity. So in order to trigger use after freeze, we need to generate an input that exercise in sequence 3 events: allocation, freeze, and use, spanning multiple functions a program under test, and the combination of temporal and spatial constraints is extremely difficult to meet in practice. The second reason is silent. So UAF bugs often fail silently, so there's no segmentation fault. So in this case, further simply observing crossing behavior do not detect that a test case triggers this bug. Before discussing our technique, so we first revise the workflow of restricted fuzzer, and so the limitation in finding use after freeze. So first, existing restricted fuzzers are distance guided, so the instrumentation phase is costly. So it spends several hours to actually instrument big programs like built-ins, and it cannot differentiate the differences between two inputs covering the same set of basic block, but in different order. Also, existing drifted fuzzer treat at least equally. However, given a set of predefined target, the likelihood of edge destination being reachable to targets are different. So consequently, in some cases, they may waste efforts exploring non-vulnerable code or infeasible path leading to specified target. And also, previous work don't take into account the orderings of cover basic block when selecting the input for mutation. They might skip input that already exercise in sequence a large number of basic block target. The the next is that use after free box fails silently. So in this case, we need to triage the own input produced by the father to find the bug triggering input. So such a large amount of unreachable input wastes a lot of time in the sanitizer by triage process. So before discussing our technique, our proposing, so let's take a look on the target. This case is just UAF or Stack Trace given by the profiling tool like Vanguard. So if we focus on bug reproduction and the path testing application, it's more likely we have a complete stack trace of own memory related UAF event. So actually in this case, there are 3 different stack traces, and each stack trace is a list of method code leading to the event. So we can extract the target location, which the pair of target function and a basic block containing a code instruction in this function. Unlike existing zero approach, we need to take into account the relationship among targets to improve the relatedness. So to facilitate our further analysis, so we first must on the stack trace in the figure on the left hand side to recreate a dynamic calling tree, and then we perform a pre-order traversal of this tree to generate a bug trace as our target. So we make sure that the trees are ordered according to the orderings of the use AF event, after the flattening process. Okay, so to address the limitation discussed above, we propose UAFuzz, which is a directed fuzzer dedicated to use after freeze by carefully tuning the key component of directed fuzzer to meet specific characteristic of use after freeze. So overall, the UAFuzz has a similar workflow, but we add some extension highlighted in orange. So first, the static pre-computation of use after free as a binary level is fast. Second, we introduce several new input metric to guide the fuzzer toward the target at one time. And finally, we triage only inputs covering the on target in sequence and pre-filter for freeze input that less likely to trigger the bug. This slide shows the key insight of our tool. So actually we select input for mutation based on similarities and orange of input trace compared to the expected trace. Then we assess the likelihood of an input based on three metrics dedicated to use after freeze at a different level of granularities, function code, hash, and basic block. So the more fine-grained the metric is, the more precise the analysis is in terms of identifying interesting input that are likely cover the expected bug choice. So we will discuss our technique in detail in next slide. So first we talk about UAF-based Distance, which is the uh, the the most important metric of directed fuzzer. So previous distances do not account for any other among the target location, while it's essential for use after freeze. So we address this issue by modifying the distance between the function in the cone graph, actually to favor the path that sequentially go through the three UAF event allocation free and use of the bug trace. And this is done by decreasing the weight of the edge in the cone graph that are likely to be between the event using a lightweight static analysis. So our distance-based technique therefore consider both calling reason in general as findable in case where the calling can appear several times at different locations in the caller uh, and the calling reason covering by UAF event in sequence. Uh, as we discussed previously, it's existing worksheet exists equally in terms of reaching in sequence target. So in this case, we propose a lightweight cut edge coverage metric by measuring the params, the progress at the edge level, but on the critical decision node only. So first, we statically identify cut edges whose destinations are more likely to reach the next target in the bug trace, as shown in the figure on the right hand side. And it's lightweight because we only perform the static intra-procedure of the control flow graph, and then at runtime UAFuzz favors input exercising more cut edges via score depending on number of cover cut edges and hit count. Next we talk about target similarity metric. This sequence-aware target similarity metric concretely assess how many targets an input execution trace cover at runtime, and also takes O-rings of target into account. So actually we combine both prefix and back option, as prefix option is more precise because it counts value until the first diversion, but actually the back option provide more information about the whole trace. And we use this metric for the state selection by selecting more frequently input that are most similar to the target bug trace. Overall, the UAFuzz assign more energy the number of mutants produced from the selected input to input in the following cases. First, the input that are closer to the target via our distance metric. Second, the input that are more similar to the bug trace using the target similarity metric. And finally, an input that make better decision at critical code junction using our cut-edge coverage metric. And then to add the triage process, UAFuzz triage the only potential input we cover in sequence on target location in the bug trace. So we obtain this kind of information for free via our target similarity matrix. For implementation, so we deploy our fuzzer on top of AFLGO, and we use the IDA Pro to get the code graph and the control flow graph of the tested binaries, and also develop the plugin in the binary analysis platform Insights for the static computation. And we also use profiling background in the triage process. For the experimental evaluation, so we evaluate our approach in two applications, bug reproduction and path testing. For bug reproduction, we compare our tool with the state-of-the-art coverage guided and with the fuzzer on 13 UAF bugs. And as AFLGO is shock-based fuzzer and Hawkeye is not available, so we implement the core techniques on our framework, and we use the metric like the time to exposure or number of bug files, the overhead, and also the number of triaging input as a comparison metric. And you can see that for the fuzzing performance, UAF outperforms state-of-the-art fuzzer in terms of UAF bugs reproduction with a high confidence level. So, for example, UAF files bug 2 times faster than the second best fuzzer. In this case, AFLB. UAF also enjoy both lightweight instrumentation time, for example, 15 times faster than AFLShort, and also a minimum of runtime overhead compared with AFLQ. So in the triage phase, UAFuzz reduce a large portion, so more than 19% of triaging input and spend only several seconds in the post-processing step. Another application of the rated fuzzer is patch testing, and in this case we aim to find incomplete patches or regression bugs and exploring around the previously vulnerable code to find new bugs. So how do we do? First, we identify recently discovered use after free bugs of the open source programs, and as the code has evolved, in some cases we need to manually extract the code instruction in the bug traces as target to guide our tool. And UAFuzz found 13 new bugs, and 4 of them are incomplete use after freeze bug fix in critical programs, and got 7 CVs. And thank you for your attention, and please check out our tool and our benchmark. So I'm happy to take any question.